And so just one special topic that I needed to finish with chapter 18, and that is KSP of sulfide. When we look in Appendix D, there's a little superscript B here for sulfide. And when we read the footnote for this, it says that sulfides are going to have a certain form for the KSP equation. That form is going to be different than all the other compounds listed in there. So let's take a look at copper 2 sulfide. If we do the KSP equation for copper 2 sulfide, it should look like this. You know, this is what we expect for the KSP. It turns out that this is not what we get for the KSP. What we get is something totally different, and that's because of sulfide. You should recognize sulfide. One of the chemical properties of sulfide really stands out. Do you know what that property is?
It's too strong for base to exist in water.
Yeah, it's too strong of a base to exist in water. And so we have this equation, but what we have to do is we have to look at the sulfide attacking water. When the sulfide attacks water, we'll form HS minus and OH minus. And this would be a combined. This is actually perfect for combined because the actual free sulfide concentration should be extremely small. One, you know, the KSP is kind of small here, and 2 sulfide immediately attacks that. This reaction is going to be very favorable because Kb is very large for strong bases. Base hydrolysis should be very large, and so you can't really stop this from happening. And so we're going to get CuS plus H2O liquid. This is going to give us Cu2 plus HS minus plus OH minus. And so this is the KSP equation for sulfides here. And so this is what we would think is the KSP equation, but this is the actual observed KSP. And so we make a little note of that, footnote B here for this. So when we look at the chart in Appendix D, they're all going to have a little superscript B referring to the footnote. Let me see if I can bring it up. Okay, this is not coming up. Anyway, this is what it'll look like here. So we know that the sulfide's too powerful of a base to exist in water. The Kb, like it said, Kb for this we call it very large, but in chapter 18 we actually want the numbers for these. We can actually get the number for this one. The Kb is actually 1 times 10 to the 5th. But we aren't going to use this number, and so this was not necessary because what we're going to do, actually this is, I need to back up here. What we're going to do for the sulfides is do it like this. So when we do a KSP type calculation for CuS, we'd set up the ice table like this, where we have the water, and then we're going to have 3 species here. And so the KSP B, Petrucci doesn't call it KSP B, but I'll just call it KSP with the superscript B, is going to be the copper 2 plus times the HS minus times the OH minus concentration. And so the equation's a little weird. Now, this will be for solubility calculations. So, you know, if we're calculating the solubility in water, it would be 0, 0, and 0, and then plus S, plus S, plus S. And so at equilibrium, we have S molar, and S molar. And so the solubility is actually just the cube root of the KSP here. That would be in pure water. But the solubility of this is heavily influenced by pH as we generate hydroxide here. And so we can see how pH impacts the solubility of this. In fact, we can see dramatic differences in solubility depending on the pH for this. And so when we're interested in how pH impacts solubility, then we want to do KSPA And so this would be a KSP superscript B with an A here. And we're looking at how acid influences this. You know, this is again acid hydronium. And so if we're thinking about acid, which of these species are going to react with acid? Well, hydroxide. It's pretty obvious. Hydroxide should react with the acid. And so this would just be our standard KSP type calculation. This would be a KSPA type calculation where we have CuS solid plus H2O liquid. This is going to go to Cu2 plus HS minus plus OH minus. Now if we have acid present, hydronium, it's going to attack the strongest base present. Well, the strongest base present is hydroxide here. So we're going to get hydronium plus hydroxide, that's going to give us 2 waters. Okay, once all the hydroxide has been attacked by the acid, the next strongest base is HS minus. HS minus being amphoteric, so it can go either as an acid or base. In this case, in the presence of hydronium, it's just going to act as a base. So hydronium can attack the next strongest base, HS minus, to form H2S plus water. All right, can hydronium attack Cu2 plus? No. We need a complexing agent if we want to attack Cu2 plus, like ammonia or something like that. And then hydronium and water will just form hydronium and water, and this is just a solid here. And so those are all the bases. Normally when we do a KSPA, there's only one base to attack. In this case, for the sulfide, there are going to be 2 bases to attack because we have HS minus, which is a base, and OH minus, which is a base. HS minus turns out to be a pretty decent base in terms of strength. And so we can add up all 3 equations. When we add up all 3 equations, we get this CuS solid plus 2 hydroniums. This is going to give us Cu2 plus H2S plus 2 waters. All right, so this will be our KSP superscript BA. Now, if we look at each equation, this is going to be our KSP equation, superscript B. If we look at this equation and reverse it, this is just KW, so it's 1 over KW. And this equation going backwards is H2S and water to form hydronium's acid hydrolysis. So this is 1 over Ka for H2S. And so the KSPAB will just be the KSP B divided by the KW divided by Ka for H2S. So now if we want to see the impact of acid, we would just plug in the initial pH here. Let's say the pH is 7, we'll plug that in, or pH of 2, we'll plug that in here, and then see what impact that has on the solubility. So typically this will be the pH 0, 0, 0. Actually, H2O is a liquid, so we have 0 and 0, and then the change, and then equilibrium. So we can see how the solubility changes with pH. But we could do that either quantitative or qualitative. For example, at high hydronium concentrations, we would expect this to shift to the right more. And so at high hydronium, it should become more soluble. In other words, at low pH, solubility of CuS should increase. At higher pH, that should decrease this. And so at higher pH, it should be less soluble. Lower pH, more soluble. Higher pH, less soluble. And so that gives us our basis for things like this, qualitative analysis. In qualitative analysis that aims at identifying cations, we aren't doing quantitative. Quantitative analysis would be interested in what cations are present and what quantity, how much. In qualitative analysis, we just care if it's present or not present. And not present is a little bit tricky. We just care if it's present. Because if you get a negative test, a negative test could mean it's not there, or it could mean that it's there, but just not in concentrations that you can detect. In other words, below the detection limit of the method that you're using. And so a positive test, for sure it's there. A negative test, it might be there, it might not be there. And that's qualitative analysis. The qualitative analysis, they take advantage of metathesis, redox, and acid-base reactions to separate and analyze the species here, the cations. Now, this is a typical qualitative analysis, how it's broken down. We didn't break it down into this, like group 1, group 2, group 3, group 4, group 5. In fact, we skipped some of the groups. I think we skipped group 2 and 3. We did this, but when we did a slightly different scheme, but this is a traditional scheme here. And so we start off with group 1, which is the chloride group. Well, the chloride group, it's just a metathesis reaction here. And so if we look at the flow chart, if we have about 25 cations here in this scheme, we only had 10. If there's silver, lead, or mercury present, those would precipitate out with chloride because those chlorides are insoluble. So this is just metathesis reaction. All the others are soluble chlorides. We end up here. And so this is what we call group 1, or the chloride groups, the insoluble chlorides. Okay, then we take the solution and then we add H2S. We add H2S at relatively high hydronium concentrations. And so this is what we call the acid sulfide group. Okay, down here, this is what we call the base sulfide group. The basic sulfide group, we have an ammonia-ammonium buffer, which we'll use to increase the pH. And so the pH of this is below 1. It's like 0.9 or something. And so if we have a pH below 1, then we'll only precipitate out the least soluble sulfides here. So these sulfides precipitate out. If we raise the pH, then we'll precipitate out the other sulfides. You know, the higher the pH, the more insoluble these become. The lower pH, the more soluble these become. And we can calculate the pHs. You know, there's a certain pH cutoff here. At these higher pHs, for example, at the lower pHs, we precipitate out the mercury, the lead, bismuth, copper, cadmium, arsenic, tin, antimony. At the higher pHs, we precipitate out the manganese, iron 2. Now, the iron 3 precipitates out as the hydroxide because the hydroxide is less soluble than the sulfide at higher pHs. The nickel, the cobalt, the aluminum precipitates out as a hydroxide, chromium precipitates out as a hydroxide, and zinc precipitates out as a sulfide. And so these are much more soluble sulfides. Of course, at lower pHs, the hydroxides don't survive. This will dissolve in acidic solution. And so we could separate those. And then the last group here is the carbonates that are separated off here. And what's left over are the soluble groups, the sodium, potassium, group 1, and ammonium salt are left over here. The carbonates are magnesium, calcium, strontium are taken out here. This is the general qualitative analysis scheme here. We'll just focus on the sulfides. Here's the chloride group. You've already done the chloride group. We didn't do lead. You know, if we had lead in there, we'd precipitate it out to chromate, get a nice yellow PPT. We had silver chloride, white PPT. We dissolved in ammonia, formed the diamine silver ion. This is a missing positive charge here. If we had mercury, and then mercury with ammonia has this redox reaction, in which we get a mix of liquid mercury contaminating the white precipitate, so it gives a dark gray precipitate. Easy to recognize. But we didn't have any lead or mercury in ours. In fact, we didn't even do the sulfides. You know, sulfide H2S is used as a precipitating agent, and so we look at the equilibria here. There's very little sulfide in H2S. It's mostly, you know, H2S. But we can precipitate out the sulfides either with H2S or HS minus, or even sulfide, minute concentrations. Again, sulfide is an extremely strong base. Its concentration in water is going to be very small. It's not stable in water, and so this is why, you know, when we're thinking about precipitating agents, you normally think about, oh, we need sulfide. No, we don't need sulfide. We just need some kind of sulfide-containing species. So H2S would work, HS minus would work, etc. So when I think about metathesis, like for example, if I want to precipitate out a phosphate in metathesis reactions, all the phosphates are the same. You know, sodium phosphate, phosphoric acid, dihydrogen phosphate, monohydrogen phosphate, all of them will do the same thing, that is precipitate out phosphates. Now, if we're talking about acids and bases, then it's different because H2S would be much more acidic than HS minus, and sulfide's a strong base. In terms of acid-base chemistry, they behave differently, but in terms of metathesis chemistry, they all behave pretty much the same. Here's some of this. Again, we aren't going to do the actual number here because what we're going to do is we're going to combine it. We're going to combine it into this equation. So if you look just at the top equation, I called KSP with a superscript B because the equation is different. When we're dealing with sulfides, you got to add the water. This is what the footnote B in Appendix D says, add the water to react with the sulfide. When you add the water to react with the sulfide, it forms HS minus and OH minus. And so this is the KSP equation for lead 2 sulfide, which is different than what you might expect. You might just expect lead ions and sulfide ions, but this is not what you get. And then what they're doing is they're doing KSPA. Acid attacks what? Well, acid will attack the bases. Acid will attack the strongest base first, so it'll be hydroxide comes first. So this is out of order. Hydronium should attack the hydroxide before it attacks the HS minus being a weaker base than hydroxide. And so, but anyway, both of them are playing strong enough to react completion. So this is what we call the KSPA equation. The KSPA equation for sulfides looks different than the KSPA equations we've done before, as does the KSP equation here. Well, we could get the number for lead 2 sulfide. And it turns out lead 2 sulfide, it depends on what the pH is. You know, very low pHs, high hydronium concentration, will be much more soluble. If we go back to the qualitative analysis scheme, you know, we're looking, this is pH about 0.9. pH about 0.9, it's still insoluble. You need way lower pHs, like closer to 0 negative, to get that stuff to dissolve. It's so insoluble. So lead 2 sulfide is really stable precipitate in regards to pH. But we can figure out at what pH will it dissolve. And so you would work backwards. Let's say we want to dissolve a certain amount, or figure out what the solubility is. Do that here using this equation. All right, that's using normal acid. Normal acids are mineral acids, but we could also use other kinds of acids. For example, oxidizing acids. If we use an oxidizing acid, then the reaction is going to be different, because in a mineral acid, you're just looking at the pH, you're looking at hydronium attack things, in an acid-base type reaction. But if we're looking at an oxidizing acid, well, now we've got to add in redox in there, in addition to the other stuff that we're dealing with. And so, for example, CuS is not very soluble, even at very low pHs. Let's take a look at CuS really quick. If you look, this is like pH less than 1. CuS it's precipitating out. And so, what kind of pH do we need? Well, maybe like 0 or negative 0.5 or something like that to get the CuS dissolved. Well, it's really tough to dissolve that stuff because it's so insoluble. And so even with this, I guess we can bump this up as well. We go to 1 molar, pH would be 0. And 0.3 molar, it's like pH is 0.9 or so. Or we could try something else, and another thing you could do to try to dissolve this, and this is a separate topic than KSPA, is this. This is not a KSPA, even though we're adding an acid. The purpose of this acid is not adjusting the pH one way or the other. The purpose of this acid is to oxidize. What are we going to oxidize? Well, if we look at Cu and S, it turns out sulfides are pretty good reducing agents, S2 minus, because they're kind of big and they got a -2 charge. And so in this case, what did we oxidize? What did the oxidizing acid oxidize? Sulfur, sulfide actually, S2 minus. And it oxidized it to elemental sulfur. And so this is just attacking it, and you can always try an oxidizer to attack it, and usually you end up with different stuff than what you would have expected. This reaction happens a lot when we're doing the full qualitative analysis scheme, which we used to do years ago. This screwed people up because they're trying to dissolve this using an oxidizing acid, but they generated sulfur. And this form of sulfur is not the yellow form of sulfur that you're familiar with. This form is a white form of sulfur, which is a polymer. It's like rubber bands. You're making white rubber bands, rubbery sulfur in there. Well, that rubbery sulfur doesn't dissolve in anything. And so you have this black PPT going to a white rubbery solid, and that white rubbery solid, people are getting confused. Is that a positive test for something or whatnot? And so you have to watch out. We could dissolve metal sulfides with an oxidizer like that, but we're going to generate sulfur, which is problematic. Well, anyway, this is another reaction that I'm familiar with. here, you know, copper 2 in water is pale blue, copper 2 in ammonia is deep, they say deep violet here. And so this is one way. Okay, so what they're saying is FES is readily soluble in strong acids, but PBS, HGS, and CUS are not because the KSP values are too low. So you got to go extreme here. Can we get a low enough pH? Probably not to get this to dissolve. Well, anyway, this is the other one, the KF. I mean, another way to do is we could do a combination attack. For example, we could do low pH. The low pH is going to help. There's more hydronium. We could heat up this stuff and shift the equilibrium to the right. But in addition to that, we could also try to attack the copper 2 as well. If we attack the copper 2, then that's going to help shift this to the right and get it to dissolve. And so one of those, before using this redox, before using the oxidizing acid, I would have done this. You know, because the oxidizing acid is going to create this. And so rather than that, I probably would have done this. I would have tried to complex the copper 2. But what would have been the problem? For example, if I complex the copper 2 with ammonia, what's the problem there? The problem there is ammonia, is it stable in acid? Is ammonia stable in strong acid? No, ammonia is a base. Strong acid will attack it, form ammonium. Does ammonium complex with copper? No, ammonium does not complex with the copper. Ammonia does. And so this is not, and so are there any complexing agents that are stable in strongly acidic solution? Not really. Cyanide? Cyanide would form hydrogen cyanide, even though cyanide would be pretty good. Oxalate, form oxalic acid. You know, all of those complexing agents are Lewis bases, and so they aren't really necessarily going to be stable in acidic solutions, so we can't really do that. However, if we don't do the acidic solution and then we go for complexing, that might work. You know, we might be able to complex this with cyanide to get it to dissolve. And so here's the aqua complex of copper 2, which is light blue. Here's the amine complex, which is this. But unfortunately, we can't do amine complex in strongly. And you don't want to. I mean, ammonia is. I don't know why they have this slide like this, actually, but because ammonia is a pretty good reducing agent. If you put ammonia with nitric acid, you're asking for trouble. This is why they say don't mix cleaners. For example, if you take an ammonia cleaner and you pour bleach in it, you're asking for trouble because bleach is an oxidizer, ammonia is a reducer. You're going to get a redox reaction. It's going to generate potentially poisonous gases. So this is a weird slide, so ignore it on the PowerPoint. Well, anyway, that was the final special topic. The special topic was sulfides, you know, the ways of getting those to dissolve. Usually try pH, but sometimes it's not successful at dissolving those. All right, we still have a couple of things to talk about in Chapter 19, although Chapter 19 is not that long of a chapter, so we're just about done with Chapter 19. So let's take a look. Did I talk about the pH meter? Yeah, I think we talked about the pH meter here. For example, did we talk about the concentration cells? Is that correct? A little bit? Okay. So the concentration cells have different applications. So, you know, here the oxidizer is the same, H plus versus H plus. So the same, H plus, in fact, these are mirror images of each other. The only difference is the concentration. On the right one, you want the concentration high, on the left one, you want it low. So if there's a tug of war for electrons, which one wins? This H plus or this H plus? Well, the one with greater numbers. And so here, the electrons will flow this way here. Doing this, we can generate a pH meter, a simple pH meter. Although you wouldn't want a pH meter like this, because a pH meter like this would be terribly inconvenient. is what you'd have to do is you'd have to bubble hydrogen gas here, bubble hydrogen gas here. You know, and dealing with hydrogen gas is dangerous and a hassle. And so this is not a good pH meter, but you know, it could be used as a pH meter. Because what's going to happen is the voltage here is going to depend on the concentration here. You know, if the concentration here were 1 molar, it's a 1 molar versus 1 molar, the voltage is going to be 0. So it depends on how great the imbalance is in the concentrations here. Therefore, we can just do this as far as the voltage is going to depend on pretty much the concentration, the power of the hydrogen, the concentration there. And so I think we did the math for that. Well, here's another example. This other example is measuring KSP. So we've got silver ion versus silver ion. Silver ion on the left, silver ion on the right. We can generate a voltage here if there's unequal concentrations here. And so over here on the right we make it higher, 0.100. On the left we make it smaller. And so this is going to be silver ion in saturated silver iodide. Silver iodide is not very soluble, so the silver ion concentration here is going to be very small. And therefore the electron is going to be pulled, actually 0.417. And so based on the voltage, the concentration of the silver ion in the cathode, we can figure out the concentration of the silver ion in the anode using the Nernst equation. Once we get the concentration of the silver ion, then all the silver ion came from silver iodide, all the iodide ion came from silver iodide. And so we could figure out the concentration of free silver and free iodide in this beaker, multiply those together, and we get KSP for silver iodide. So that's a homework problem you can try out. These are alternative electrodes. Like, for example, this is what they call the modern pH electrode here. The modern pH electrode doesn't even have this solution in here and all this other stuff. You know, this glass membrane. Glass membrane is subject to drying out and also has some response issues. Now they're using little silicon chips. You know, and these silicon chips, they have some amorphous silicon, which is sensitive to hydrogen ion concentration. So totally solid state electrodes versus these, which require wets. But these are all different kinds of electrodes here. Some of these electrodes are kind of funky, like silver. Here it's a silver chloride, and so it's kind of a weird half reaction there. And then we got the mercury, and the mercury 1 chloride, and silver chloride HCl class. And so we've got some different electrodes with different half reactions there. And the half reactions were chosen to give a specific response. But we aren't going to get into these other electrodes. This is a glass electrode for pH measurement, which is silver chloride in there. Silver chloride is your oxidizer, solid silver chloride. And then silver metal is your reducer here. Essentially, we get the same cell potential as 0.0592 volts times pH, or pH is cell potential divided by 0.0592 volts. But this response isn't always accurate, and so normally what we do is we calibrate it. You know, we don't calculate it. There are like, for example, in the LabQuest, there's a fixed slope in there that they put in, but it's better just to calibrate it manually, you know, in case it's not responding correctly. Okay, then that's the electrodes, some of the more complicated electrodes. We talked about the batteries. Basically, two more topics that we need to talk about in chapter 19. One is corrosion of iron. Corrosion of iron is more complicated than it appears, because when we're thinking about rust, we think iron metal is being oxidized by oxygen to form iron oxide or iron trioxide solid. So this balances 2 irons, 3 halves of O2. And so this looks like the reaction. You know, we just have rusting of iron. Oxygen is the oxidizer here, but it's actually a bit more complicated than this. and this slide showing a little bit of that. And how is it more complicated? And so, actually, this is a voltaic cell. And when we look at it, let's take a piece of iron here. If we have a piece of iron here, then oxygen is going to come in as the oxidizer. When the oxygen comes in, it's going to try to take electrons from the iron. But the reaction is a bit more complicated than that. You know, for example, the dry iron versus wet iron. Do we need moisture around? If the iron's totally dry, does it really corrode and rust? Totally dry. No moisture around at all. And the answer is no. I mean, it could, but it'd be extremely slow, and we wouldn't have a corrosion problem. It's just if there's moisture around, we're going to have a corrosion problem. And the corrosion problem is this, because we need that moisture around here. Like, for example, there's got to be some H2O. In fact, we'll put in 2 H2O liquids. And so let's say there's some water around here. And the H2O and the O2 are going to take 4 electrons here. And so we'll get 4 electrons come in here. And so if we have 2 H2Os, an O2, and 4 electrons, we're going to produce 4 hydroxides here. And so this is the cathode reaction. The cathode reaction is oxygen's the oxidizer, but we need some water present. The reason we need water present is so that we form hydroxide, because if there's no water present, we form oxide. Well, forming oxide's okay, but what's more stable, oxide or hydroxide? Oxide or hydroxide as a base? Which one's a weaker base, oxide or hydroxide? Oxide is a stronger base. In fact, oxide is just like sulfides. You know, although Petrucci didn't do this, we could have said the same thing about metal oxides. If we're looking at KSP for metal oxides, we're going to form, like, let's say we're doing copper 2 oxide. If we're doing copper 2 oxide, what's the KSP equation for copper 2 oxide? The KSP equation is copper 2 plus oxide. Have you ever seen oxide AQ anywhere? Yeah, there's good reason you've never seen oxide AQ anywhere is because oxide is what we call too powerful of a base to exist in water, and it's going to hydrolyze completely. I mean, Kb for oxide is very large. And so the same thing here for copper 2 oxide is we end up with copper hydroxide, not copper and oxide, because oxide is too unstable, right? Too reactant. Although Petrucci doesn't have any oxides in Appendix D, he just has sulfides. And the same type of deal would happen with oxide because oxide is a powerful base. You should know the powerful bases. What are they? Amide, sulfide, and oxide. Those are 3 bases that are more powerful than hydroxide. Well, if water isn't present, what would we form? We'd form oxide. Is oxide very stable? No. Is hydroxide? No, hydroxide is very reactive, but hydroxide is a lot more stable than oxide. The problem is how the oxidation takes place, you know, because the oxygen can come in anywhere, and it does come in everywhere. But the iron, you know, this is a metal. And metals conduct electricity, right? The electrons move freely in metals. And so the oxygen might attack the iron here, and it'd be great, because if the iron here were oxidized, then we're okay. We could just go ahead and form oxide, because we'd form iron 2 or iron 3 oxide. It'd be stable. But the situation is this. The oxygen is going to come pull electrons off, but where are those electrons going to come from? And not all the irons in iron metal are equal. Did you know that? Some iron metals are going to be less stable than others. For example, if I have an iron at a corner here, is the iron at the corner as stable, as tightly bonded as an iron in the middle of the surface? No. No, because iron at the corner is not held together or bonded to as many irons as an iron on the surface. Is an iron on the surface as stable as an iron in the bulk, in the center? No. Do you guys remember surface tension? The water molecules on the surface have a higher energy than the water molecules inside the liquid. And that's because the water molecules on the surface have less bonding. And so even though the oxygen would like to oxidize this iron here, because of the electron, it's going to oxidize, not that one, it's going to oxidize the irons at what we call defect sites or corners or edges. And so a defect site could be caused by, let's say you have a dent in the car. If you get a dent in the car, is it going to start to rust at the dent, or will it start to rust in the pristine part of the iron? It's going to start to rust at the dent, because that's where you created a lot of defects, creases, or holes. And so any kind of defect here, let's say there's a defect here, these irons are the ones that are going to lose the electron, even if the oxygen's pulling. The oxygen's trying to oxidize this iron here, but this iron here is stable compared to these two. And so what's going to happen are these 4 electrons are going to come from these 2 irons here going to iron 2 plus and iron 2 plus here. All right, there's another reason we need the water. Because iron 2 plus is not stable in air. Iron 2 plus aqueous would be a lot more stable. And so there's got to be water here, or moisture here. So we've got to extend the water out down. But then we generate space charge, right? If we generate space charge, what's going to happen? The reaction is going to stop. And so the only way to eliminate the space charge is to neutralize it. Well, we could have 2 things. We could have DI water. Does iron rust very fast in DI water compared to salt water? What do you think iron corrodes faster in, salt water or DI water? In salt water. If we had DI water, corrosion would be very slow. The reason corrosion is very slow in DI water is because the only way to neutralize the space charge here is that the hydroxide and the iron 2s have to migrate to each other to neutralize themselves. And so what moves faster, hydroxide or iron 2? What moves faster, hydroxide or iron 2? Well, it's like diffusion. If you're looking at gaseous species, what moves faster? Do you guys remember diffusion? The rate of diffusion is equal to the inverse of the square root of the molar mass. And so diffusion depends on the mass. So hydroxide is a lot less massive, a lot lighter, so it moves faster. So eventually the hydroxide will move rapidly towards the iron. Iron 2 will move slowly towards the hydroxide, and then they'll neutralize each other out. But if we have salt water, then we don't have to have as much diffusion occur so rapidly, because if we have salt water, let's say sodium chloride, then the sodium ions will stabilize the hydroxide, and the chloride ions will stabilize the iron 2. So with a salt bridge, then this could corrode much more freely. And so DI water, we need water. Dry iron doesn't really rust. And so if it's wet, it will. If it's wet with DI water, it doesn't really rust that fast. If it's wet with salt water or minerals, if there are minerals in there, then it's going to rust much faster. And so it's because of this. cell. Now, does iron corrode faster in acidic or neutral solutions, do you think? It corrodes much faster in acidic solutions. That's because of this. If we look at oxygen here, oxygen is our oxidizing agent. So oxygen reacts with the water and pulls off 4 electrons, the iron, to form 4 hydroxides. If this were an acidic solution, we'd have a different reduction reaction. The different reduction reaction would be oxygen plus 4 H pluses plus 4 electrons. This is one in Appendix D. This one's in Appendix D, but not in this chapter. Gives 4 waters. Now, what's more stable product, 4 hydroxides or 4 waters? 4 waters. And so what we're going to say is that oxygen in acid solution has a much higher or much lower reduction potential than oxygen in water. Oxygen in acid has a higher reduction potential. And so this reduction potential here is 1.229 volts. That means the reduction potential up there at the top equation must be lower, probably significantly lower than 1.229 volts. In fact, we could look it up if pull it up in Appendix D, but it's not coming up right now, so we'll skip it. But anyway, so if we have a higher reduction potential here than here, that's going to give us a larger cell voltage, which means a bigger driving force for corrosion. And so these are the things. Iron corrodes faster in wet versus dry. Iron corrodes faster in salt water versus DI. Iron corrodes faster at low pH or acidic conditions than at neutral. Let's see here. So here's some corrosion. Let's look at the Petri dish here, A. If we look at this one, this is an iron nail. This is not galvanized. What they did was they hammered the ends. When you hammer the ends of an iron nail, you create lots of defects, right, and other things. And so what's going to happen here, and they put some phenolphthalein, this water in here, salt water. They put phenolphthalein in here. They put phenolphthalein to detect where the hydroxide. Actually, this is not salt water. This is just plain water. It's plain water because we're generating hydroxide. If there was acid in there, we'd be generating water. But anyway, we're generating hydroxide here. So the oxygen is coming in here and pulling the electrons. Oxygen is coming here, pulling the electrons. We're forming hydroxide. Hydroxide turns phenolphthalein pink. But where are the electrons coming from? The electrons aren't coming from here. The electrons are coming from the ends. Because that's where the easiest to oxidize iron is. And the easiest to oxidize iron, what do we call that? The iron here in the pristine part of the nail versus the iron here in the damaged part of the nail. The iron at the damaged part is going to have a higher, what? Well, we call it oxidation. The iron here on the ends will have a higher oxidation potential than the iron in the middle because of the defects that were introduced into the structure. And so take a look closely. It's hard to see in this picture, but do you see green precipitate around here? Can you see the green precipitate? No? Let's see. Do you see the green precipitate growing on the ends? No? All right, just take my word for it. There's green precipitate on the end. What do you think? You know what that green precipitate is? Iron 2 hydroxide. And so the hydroxide moves rapidly because it's not very massive. Iron barely moved at all, and the hydroxide is precipitated here. So hydroxide is going to precipitate around here. And so the middle part of the nail, we call that the cathode or the anode? Middle part of the nail. Well, actually, cathode. The cathode is where reduction occurs. And on the ends, we call that the anode. So this has 2 anodes and 1 cathode. In other words, corrosion is happening at the anode, because the electrons are being generated. Oxidation occurs at the anode, reduction occurs at the cathode. This is the same thing. In Petri dish B, they took a nail, And they folded it in half. If they fold it in half, what you can give here, you can create lots of defects here, and make that susceptible to corrosion. So what's susceptible to corrosion are the hammered ends in the corner here. And so again, here we have two cathodes, cathode here, and 3 anodes here. That's because again, the defects in the structure are going to cause the iron to have a higher oxidation potential. It'll be easier to oxidize. Well, what if we wrap zinc foil around it? If we wrap zinc foil around the nail, then take a look. This is pristine nail. This is a pristine nail. And so it looks like the iron is the cathode, like it was before. But what's the anode? The anode is now zinc. You see? The zinc is being corroded. In fact, you can see, do you see white zinc hydroxide PBT here? Well, you can see it in your book. There's white zinc hydroxide precipitate around this. And in other words, here, zinc has a higher oxidation potential than iron. And therefore, the zinc is going to be oxidized. This is what we call a galvanized nail. Galvanized nails are zinc coated or zinc wrapped nails. And usually they coat it, so they'll put it in molten zinc and get a nice even coating of zinc. What happens is it protects the iron. The iron's the structural part. You need the iron to hold the wood or whatever you're nailing together. And so you want the zinc to corrode, not the iron. Well, what if we wrap copper around the nail? If you wrap copper around the nail, then what's going to happen here? Well, in this case, the copper will be the cathode here, and what has the highest oxidation potential? Well, the entire nail compared to copper. So the nail will be corroding. So copper is not going to protect your iron. The zinc will. Anything with a higher oxidation potential than iron will protect it. We call that a name. Talk about here. We call it a sacrificial anode. And so here's a little diagram here. Here's our cathode. The oxygen and the water come along, forming the hydroxide. Hydroxide turns to paint. And so here's the iron. And so we just need zinc attached to this. If there's any zinc attached to this, then the zinc having a higher oxidation potential will be oxidized. The zinc has to be in electrical contact with the iron, so the electrons can travel. Iron here. So here we're going to have corrosion of zinc instead of the iron. And that works until all the zinc is eaten away. Once all the zinc is eaten away, then the nails will start to corrode. So, copper, on the other hand, is not effective. Copper has a lower oxidation potential than iron, and therefore iron is going to be oxidized, not copper. Copper is thought, like copper-plated iron, people are thinking they can plate it with an inert. Because copper is not really susceptible to rust, although sulfate formation of sulfides, yes, not rust. And so, but the problem is if there's any break in the coating, then the iron's going to rust. Because here we'll have our cathode, iron will be the anode. We don't want the iron to be the anode because the iron is what supports the structure. And so we want to protect the iron. The copper plating doesn't work, but the idea is if you could plate this, if there was no break here, then it would work. As long as the iron is not exposed to moisture or outside, then we're okay. And so this is the whole idea behind painting. Painting helps protect the iron. The way paint helps is just to give it a coat so that no iron's exposed. Problem is if there's a chip in the paint, then forget it, it's going to start to rust. Just like copper. Copper is very expensive compared to paint. Paint's much cheaper. But paint doesn't last as long as copper, but if there's any kind of chip in the copper, then forget it. All right, here's some galvanized nails on the right. Those are all coated with zinc. You can see the silver zinc coating on there. And so the zinc will corrode. But this has a finite lifetime because once all the zinc is corroded, then the nail will corrode. What they do on things that are more expensive, like boats, is they can use sacrificial anodes like this. This is magnesium. Magnesium has a high oxidation potential like zinc, and so it's easy to oxidize. And so they just attach some magnesium blocks here. Actually, they sell sacrificial anodes at Home Depot. You can buy magnesium blocks to protect your gas lines and other plumbing. So you can do this yourself if you want. Okay, but here, obviously this is going to be underwater here, so this is going to protect the steel. It's still corroding. Let's see it here. Lots of corrosion. Now we're forming the hydroxide, but the hydroxide is easily oxidized. You know, if we form iron 2 hydroxide, which is the green precipitate, then the iron 2 hydroxide can be oxidized to iron 3 oxide rust without too much difficulty. It's pretty easy to oxidize. Okay, any questions on corrosion? Corrosion, we call this cathodic protection. You want to protect the cathode, which is iron, or sacrificial anode. It's the same thing. Cathodic protection, sacrificial anode. And so here in the boat, they sell steel ship providing cathodic protection against corrosion. Well, because we have magnesium sacrificial anodes. All right, the last topic of chapter 19 deals with electrolysis. Electrolysis is using electricity to drive non-spontaneous reactions. And so this is a spontaneous reaction here. Zinc and copper 2, we built this battery here. Got a voltage of 1.1 volts. But what's going to happen is this battery is going to operate and the voltage is going to decrease, and eventually the battery is going to go dead. This is a rechargeable battery, though. This one's not too difficult to recharge. We could recharge this by forcing the electrons backwards. If we force the electrons backwards, we're just going to reverse the reaction. That is, we're going to take solid copper and Zn2+ to form Zn solid and copper 2. You know, and so we're going from weaker to stronger. When we go from weaker to stronger, we say there's no driving force. And we get a negative voltage, negative 1.1 volts. But we can force this reaction to occur. The way we force this reaction to occur is hook it up to a power supply or a battery. And so in this case, we have a power supply or battery here. For the power supply or battery, we put the positive terminal on what was the cathode. And the positive terminal, as long as we have a high enough voltage, what this is going to do is it's going to suck electrons into it. And so it sucks electrons into it, thereby oxidizing. The copper is going to be oxidized to copper 2+, so we're going to regenerate a copper 2+. And then over on this terminal, we have its negative terminal is generating electrons, so it's going to force electrons into this electrode here, which is going to reduce something. It's going to reduce whatever has the highest reduction potential. What has the highest reduction potential in this case would be Zn2+. And so Zn2+ is going to be reduced back to zinc metal. And so we regenerate the cell by recharging it using electrolysis. So here we're recharging this battery. Some things here. You know, it looks like we just have to apply a voltage of 1.1 volts in the reverse direction. But it turns out we have to apply more than that because of something called overpotential. A voltage significantly in excess of the calculated value may be necessary. It depends on how the reaction occurs. We also have to watch out because we think we're reversing it, but competing reactions might pop up, and these competing reactions might pop up and
upstairs.
Yeah, and so you might not get the reaction that's desired. Reactants are often in non-standard states, so we have to use the Nernst equation. The nature of the electrodes matters. It matters for everything. And so that was recharging a cell here, but a lot of electrolysis involves generating reactive chemicals, like sodium metal and chlorine gas. And so we could set up an electrolysis cell here. Electrolysis cell can be 2 beakers or it could be 1 beaker. And so we could do 1 beaker setup here, and electrolysis of sodium chloride molten. So if we look at liquid sodium chloride, NaCl liquid, we're going to put in 2 electrodes here. this. And then we're going to put a power supply here. The positive end, the power supply, is going to suck electrons into this one. And so what we have to do is we'll use platinum here, solid. We have to look at what's present here. And we're going to oxidize something here. And so we got to look at the oxidation potential. And so what has the highest oxidation potential on the right? Is it the platinum, or is it the sodium, or is it the chloride? And so why don't you rank them in terms of oxidation potential? Do the same thing over here in terms of reduction potential. Rank them in terms of highest oxidation potential and highest reduction potential. Just from knowledge. So what did you come up with as far as oxidation potential? What do you think has the greatest oxidation potential and the lowest? Your three items. Rank it. What would you? The strongest reducer would be platinum.
Oxidation agent? We're not on the charts, we kind of have to.
No, I know. That's why you have to use your chemical knowledge to figure this one out.
Sodium to the weakest.
Okay, let me ask you this. If you're in a swimming pool and you have platinum jewelry, do you worry about chlorine attacking your platinum jewelry? Well, what do you think? Do you think? Because if chlorine attacks your, let's say chlorine oxidizes your platinum jewelry. If chlorine oxidizes your platinum jewelry, and platinum is so expensive, would you want to go in a swimming pool with anything that contains platinum or gold? No. So what do you think? Do you think chloride is a stronger reducer than platinum? So you said platinum has the highest oxidation potential, would be the strongest reducing agent,
I think so.
right?
Yeah.
Okay, and then chloride, and then what, sodium ions?
Yeah.
Is that the ranking?
Are we going
And then, there's no water in this one. This is molten sodium chloride, there's no liquid water. Does that look right? In other words, platinum would have the highest oxidation potential, chloride the next, and then sodium the next? Yeah? That sounds about right, because, you know, metals should have a high oxidation potential, right? Metals should be easy to oxidize, but is platinum easy to oxidize? Maybe, let me show you this. This is what happens when you look at the chart a lot. If you look at the chart a lot, copper, what can oxidize copper? Will tin 4 oxidize copper? Will tin 4 oxidize copper? Well, actually, let's not do this copper. Let's do the other copper. Oh, that's right. This chart is screwed up in this way. But it's okay. We can still do it this way. Will tin 4 oxidize copper? Will copper oxidize copper? No, we need a stronger oxidizer than copper to oxidize copper, right? And that means iodine. Iodine will oxidize copper. Tin 4 will not oxidize copper. Okay, now what you have to do is you've seen this chart so many times that you could say this. Copper versus tin 2, which one's a better reducer? Tin 2 or copper? Tin 2 is a better reducer. And so this is what I'm saying. If you take the conjugate of chloride is chlorine, will chlorine oxidize platinum? What do you think? Will chlorine oxidize platinum? Probably not, because otherwise, you know, if you're in a chlorine swimming pool, you probably wouldn't want to wear a platinum ring or whatever else. And so what we're saying is this. If that's the case, if chlorine will not oxidize copper, then the species with the highest oxidation potential should be chloride. Chloride's going to be easier to oxidize than platinum, and sodium ion the least. And so the electrons aren't taken from the platinum, the electrons are going to be taken from the chloride, because chloride's going to have a higher oxidation potential than platinum, and it means we're going to generate chlorine gas here. Platinum's really pretty inert stuff. Now, what has the lowest reduction potential? What has the highest reduction potential? Can you rank these species? We're going to use platinum again. Can you rank these in terms of reduction potential from lowest to highest?
Sodium's the highest reduction potential.
Yeah, sodium would be the highest reduction potential.
And platinum and chloride is the opposite, right?
Platinum and chloride, yeah, it would be the opposite. And so sodium has the highest. And so what that means is that the sodium is going to take the electrons and it's going to form sodium. But at this temperature, you know, it's hard to melt. Have you ever tried to melt table salt? It's hard to melt. It's got to be high temperature. And so if we're forming sodium metal, it's going to be molten sodium metal, sodium liquid. And so this molten sodium liquid will form a pool of sodium. Therefore, we need some kind of barrier here. There's got to be a barrier here, because we don't want molten sodium coming into contact with chlorine gas. If molten sodium and chlorine gas come together, you're going to get an explosion. And so this is it. And so this is an electrolytic cell. For this, we just have to turn up the voltage until this happens. And let's go back to this. So what's going to happen at the reduction is going to happen at the cathode. And so this is the cathode, this. And this is the anode. For electrolytic cells, we write them backwards. There's a cathode on the left, anodes on the right, and electrons flow backwards, flow the opposite direction. And so here at the cathode, we're going to have sodium, liquid sodium form. At the anode, we're going to have chlorine gas form. And so we're going to be able to make these highly reactive elements, sodium and chlorine. If we do this in aqueous sodium chloride, reactions are different. In aqueous sodium chloride, well, it's because we have one more species in there. And if we look at aqueous sodium chloride, we don't have to heat it so hot. And so that's a huge advantage because molten sodium chloride requires a lot of energy to melt that. But whereas aqueous sodium chloride, we get sodium ions, we get chloride ions, and we can do this at room temperature. But we have one additional disadvantage, and one additional disadvantage is we also have water. To worry about the water. Okay, we can do this in one pot here. And so we'll put a platinum electrode here, we'll put the power supply here, and then we'll put a platinum electrode here. Okay, now the electrons are being sucked into the power supply here, so this is going to be the anode of this. And so at the anode, oxidation occurs. What species has the highest oxidation potential? And so what are the species we have? We have platinum, we have sodium ions, we have chloride ions, and we have water. And so out of these species, which one has the highest oxidation potential? And so let's take a look at that. Let's see. Well, what has the highest oxidation potential on the redox chart? What has the highest oxidation potential on the redox chart? Lithium metal. What's the oxidation potential of lithium metal? Lithium metal's oxidation potential is plus 3.05 volts, right? Because oxidation is going backwards here. So plus 3 volts for lithium. And so let's go down the list. Or up the list in this case. The first species we hit is water. Well, the oxidation potential of water is plus 1.229 volts. And then chloride at plus, actually this is wrong. Water should be minus 1.229 volts, and chloride should be minus 1.36 volts. So minus 1.229 versus minus 1.36, well, minus 1.229 is higher. These two, platinum is off the charts, sodium ion is way off the charts, because the oxidized sodium ion, you'd have to pull a core electron off. And pulling a core electron off is not easy to form sodium 2+. So sodium plus is definitely the lowest. And so the ranking would be, water would be the highest, chloride the next, platinum next, and then sodium ions the last. Terribly difficult to oxidize sodium ion. All right, so at this electrode, the power supply is pulling electrons. It should pull electrons off water. Water should be oxidized. When water is oxidized, what's produced? When water is oxidized, it produces oxygen gas. And so we should produce oxygen gas here. In fact, we shouldn't be oxidizing the chloride. However, this is one exception you have to memorize. The one exception you have to memorize is this. Water has a higher oxidation potential, but if there is a competition between chloride and water, chloride wins. Chloride wins. Why is that? The reason why chloride wins is because of this. You know, it has to do with energy, and one way we can think of energy is like this money analogy. So, for example, here, Sometimes if you do like, let's say you do an investment, sometimes you have to invest money to make money. Have you heard that? Invest money to make money? Okay, that's investment, right? And so here it turns out that for water, we could make more money, but the initial investment is much greater. For chloride, the initial investment is much smaller, but you also don't make as much money. And the initial investment is what? The initial investment is of energy. For water, look at what has to happen. We go from liquid water to oxygen, gas, and H+. The water molecules are completely destroyed, broken apart, and rearranged. For chloride, are the chloride atoms completely destroyed? No. What happens is you just pluck off an electron from the outermost shell. And so the initial investment to oxidize chloride is minimal. You don't need much. The initial investment to oxidize water is huge. You need a lot of energy to input to get this out, because the water molecule has to be completely broken apart and rearranged. And so which one is easier? Well, it depends on how much money you have to invest. If you don't have much money to invest, that is, you want to do it by minimum input of energy, that is minimum input of voltage, then you're going to have to go chloride. However, if you have something that's super powerful, like a tremendous power supply that's going to rip electrons off anything it comes into contact with, then probably going to form both. You can form the oxygen. And so what happens here is this. You have to memorize that, yes, this is expected to be oxidized, but chloride wins because of what we call this. Let's see what the trick sheet says here. All right, so two possible oxidation half reactions here. The two, well, actually there's more than two. I count 4 possible oxidation half reactions, right? And the two most likely oxidation half reactions are these two. These two are highly unlikely. And so there are 2 likely reduction reactions. Actually, let's skip that. 2 possible oxidation. There are 4 possible oxidation. Of the 2 that are most likely, as far as oxidation goes, would be chloride versus water. Water should win, because it has a higher oxidation potential, but chloride wins. Chloride wins. That's because the overpotential is the initial investment in voltage. You have to crank up the voltage even higher than what's expected to get it. And so because of this overpotential, that is, it's harder to oxidize water initially than it is chloride, even though the amount of return you get in terms of energy is less. This is the kinetic aspect. And so chloride, you have to memorize. Chloride versus water. Chloride is oxidized. In terms of chemistry, we call this, the chloride has a lower activation barrier. Activation barrier is the amount of energy you have to input. It's your initial investment. And so it has a lower activation barrier and an easier mechanism. And so it happens much faster. And so chloride is oxidized. Even though water is expected to be. And so what's going to happen here is this. Chlorine gas forms over here. And so, okay, chloride will oxidize even though water is predicted, H2O is predicted. To be oxidized. We call this kinetics. These voltages are thermodynamics, and then there's another aspect of reactions, and that's the speed of the reaction. Chloride, that speed of the reaction, the oxidation is going to be much faster than water. Water is to break things apart. All right, that takes care of the oxidation. Let's look at the reduction. So electrons are being forced onto this electrode. They're going to reduce the species with the highest reduction potential. So what has the highest reduction potential? Well, what are the species here? We have platinum, we got sodium ions, we got chloride ions, and we have water. And so out of these four species can be reduced. Out of those four, what will be reduced? Well, what's going to be reduced is the species with the highest reduction potential. Which has the highest reduction potential? Well, we can go to the Appendix D and take a look. The highest reduction potential on the chart is fluorine. And so we'll start off with fluorine and then just work our way down until we encounter some of these. The first species we're going to encounter is sodium ion. Sodium ions here. Just make a note of it. Sodium ion's reduction potential is minus 2.7 volts. Okay, then let's keep going down the chart. As we keep going down the chart, we'll encounter water. Here, water. But this is in a second chart, and so the water's reduction potential is minus 0.828 volts. So sodium ion is a minus 2.7 volts. Water is minus 0.8 volts. What's chloride's reduction potential? Is chloride's reduction potential minus 1.36 volts? Is that chloride's reduction potential? Minus 1.36 volts? No. That is chloride's oxidation potential. Chloride's reduction potential isn't even on the chart. As we're looking for chloride on the left-hand side, I see chlorine. Chlorine has a good reduction potential because chlorine wants electrons. Does chloride want electrons? No, chloride does not want electrons. Where do the electrons go? If chloride gains electrons, it's going to go in the next shell. And the next shell is going to be high in energy, so it will form Cl2 minus, which is unfavorable. And so chloride, it would be ranked like this. First water, then sodium, then platinum, then chloride. Chloride would have the lowest. It'd be off the charts low. And so here it's obvious. Which one has the highest reduction potential? Water. And so what's going to be reduced? Water. When water is reduced, it forms hydrogen gas. And so at this electrode, we're going to bubble hydrogen gas. And so if we're trying to form sodium, we can't have water around. If we're trying to form the element sodium, if water's around, water has a higher reduction potential, and water would be reduced over sodium ions. And so we've got to be careful here because we get a different reaction. Well, the hydrogen gas and the chlorine gas have to be separated by a physical barrier, otherwise we're going to have an explosion potentially occur. And so the two half reactions here are this. Water is reduced here. I moved it. I'll just copy it down. Water is reduced. To 4 hydroxide. Is that right? Is it balanced? 2 hydroxide, sorry. And chloride is oxidized. And then that would be it. And so these are examples of electrolytic cells. Let's take a look at the actually, that wasn't the final topic. This is the final topic. And that is stoichiometry. This stoichiometry is not just for electrolysis. This stoichiometry is for both electrolysis and voltaic cells. And in order to do the stoichiometry, all you have to know is the time and the current. And so let's look at cell stoichiometry, both electrolytic and voltaic. And so for stoichiometry, we need to know the Faraday. The Faraday is 96,485 coulombs per mole of electrons. And then we need to know the definition of the amp. 1 amp is a coulomb per second, 1 coulomb per second. And so with this, we can do stoichiometry on any cell by measuring the current. The current is the amps. And so let's say calculate the grams of copper solid deposited when a cell operates for 10 minutes at 560 milliamps of current. This is just straight stoichiometry where we start off with a given 10 minutes, and then 560 milliamps would be 0.560 amps. 0.560 amps is 0.560 coulombs per second. And so I have minutes here. I got to convert that into seconds. Sorry. And so there's 60 seconds per minute. So minutes cancel, seconds cancel. That leaves us with coulombs. If I have coulombs of charge, then I know how many coulombs pass through in 10 minutes. Then I can convert that into moles of electrons. 96,485 coulombs per mole of electrons. And then I need the half reaction. Copper 2 plus 2 electrons goes to copper solid. And so this is going to be one of the half reactions that occurs. So we see the balance here. That is 1 mole of copper solid here for every 2 moles of electrons. And then copper weighs 63.55 grams per mole. And so we can do cell stoichiometry like this. That is, we can go from time to coulombs to right, and then there's some final stuff here. This is refining or purifying copper by electrolysis. This is electroplating, plate copper or whatever other metal. This is generating sodium and chlorine. This is an A cube, so how do they get around water? Well, they have some kind of mercury electrode, liquid mercury electrode. And so it's very ingenious. Here they don't have to heat it. You just use room temperature. All right, that's the end of the chapter. The
Do you have class
yeah. For tomorrow is the computer lab, but we're going to meet in the regular lab first. We're going to go over the computer lab. I have to talk about kinetics a little bit.
Wednesday, the start of a new chapter.
Tomorrow. Tomorrow we're starting chapter 20. Well, we already started chapter 20.
Are you going to be working on chapter 20 on Wednesday then? Because I'm not going to be Wednesday. So
Yeah.
just work on chapter 20.
Yeah, we're going to talk about chapter 20.
Okay.
I'll record it and
All right, I can
post
get
it.
notes on it.
Yeah. Hello? Yeah. After. Yeah. Now. Yes. She's expecting Paula to drop off, and Paula is at the gate. Okay. Bye. Oh, okay. Thanks. I'll take a look at this. We'll talk to you tomorrow.